Welcome back, AP Statistics. We are going to shift gears today and talk a little bit about quantitative data as opposed to categorical. We are going to look at some graphical displays for quantitative data, specifically dot plots, stem plots, histograms, and ogives. Last but not least, we're going to start referencing something called shape of quantitative distributions, and we'll talk more about that in the coming days. All right, so there are actually 5 types of quantitative data. We are going to talk about these 4 in particular today. There is also a box plot, which many of you probably were exposed to in Algebra 2, if not in other places. But we are going to leave that for another day because it goes nicely with some other material as well. All right, a dot plot we're not going to spend too much time on because it's relatively self-explanatory. I love when the name makes sense with the graph. To construct a dot plot of the following data, we have quantitative measurement, how long it takes for people to eat their breakfast, and we have a certain amount of people that responded with each data value. So I'm going to set up similarly to a number line along the x-axis, 1 all the way to 12, and I'm going to put dots above each of those values to represent how many people responded with that particular outcome. Couple things to notice. It's important that we have equidistant units. We have our axis labeled. We have a title. We are clear on units. And not only are we clear on units, but we are clear as to how many people in this case each dot represents. It's typically assumed that it's 1, but you can technically let a dot represent more than 1 as long as you're consistent. 2 little things to be aware of. Please make sure when you do dot plots that you keep your dots equidistant and you keep your dots consistent in size and shape. We don't want our eyes being confused by other characteristics. All right. Next, we're going to shift gears to a stem plot. This might be a less familiar of the graphs that we're going to talk about today. So go ahead and take a look at this little video and I will follow up with a couple questions. How to construct a stem plot, plus a few tips and tricks. The first thing that you need to be able to do in order to construct a stem and leaf plot is to identify the leaf portion of your data and the stem portion of your data. Now, the leaf portion of your data is always going to be the smallest place value. Now, in this case, my smallest place value of all these numbers is going to be the ones place. So what I'm going to do is I'm going to draw a vertical line separating the ones place from the rest of the values. All the values to the left of this line are going to act as our stem. We have our leaf portion in the ones place, stem portion, all the values to the left. Now with this first example, I want you to notice that not all our data values have the same number of digits. For example, we have numbers like 99 and 87 versus 104 and 146. Now, the ones place is the smallest place value in all of these numbers, so the ones place is going to act as my leaves. Now, what I want you to notice is that our stem values, everything to the left, some of them have 2-digit stems, some of them have 1-digit stems. That is perfectly acceptable. Our leaves are the only values that have to remain 1 digit. Now, in this case, you'll notice that my smallest stem is an 8, and my largest stem is a 20. So my stem and leaf plot is going to have a stem ranging from 8 all the way to 20. Notice my leaf unit is the ones place, so that is just a unit of 1. Now for this next example, our ones place is still our lowest place value, so that's going to still distinguish my leaves from my stem. But I want you to notice 7 and 9. It appears that they don't have a stem. However, they actually do. If it appears that they don't have a stem or a leaf according to the way the data is split up, what I want you to do is I want you to place a 0 as a placeholder. Now I can clearly see that my stems range from 0 all the way to 6, and my leaf unit is still the ones place. In this last example, I'm going to show you a case where there's some decimal places. Now notice my smallest place value in all of this data set is the first decimal place, and so that first decimal place is going to act as my leaves. Now what I want you to notice is that down here it originally appeared that we did not have a leaf there. We did, however, we just had to input a 0. Now I can clearly see that my stems range from 95 to 99, and my leaf unit is 0.1 in this case because it's the first decimal place of my leaves. So I'm going to do that for the percent of females who are literate from our previous data set. Now to construct a stem plot, I first need to identify my range of my stems. So I'm going to clearly look at all my data values and I'm going to identify what my range of stems, in this case being my smallest stem value is a 2 and my largest stem value is a 9. So my stem is going to range from 2 to 9. I'm going to use that information to set up the left side of my graph. See, my smallest stem is 2, largest stem is 9, going vertically. Now the second step is to go through the data and write each leaf on the proper stem. Now it's important to note that this number 318 is not 318. Each leaf is attached to its appropriate stem to be its own value. And what I mean by that is, for example, this number is 29, this is 31, then we have 38, 46, there's no 50s values, then I have 60, 63, here's another 63. So it's important to note that each leaf is attached to its stem separately. Now, trees grow from the stem out, or from the trunk out, and they get larger as they expand further and further away. Now that's important to note because that tells us that we're going to reorganize our leaves so that they grow out almost like a tree would, and as they get further away from the trunk or the stem, they become larger and larger. So you'll notice that our values now go in order from the stem out. So in this case, I have 7, 0, 1, 1, 8. As I read left to right, my leaves get larger. Now the last thing to do in order to have a properly constructed stem plot is to just properly label it. So I'm going to put a nice title on here, clearly identifying what the stem plot has to do with. And then I'm also going to incorporate my leaf unit, in this case showing that each leaf represents 1%. And that would be a well-designed stem and leaf plot. Now a little trick, we're not going to quite get to describing them yet, but for when we do get to that point, I want to show you something that you can easily do with your stem plot in order to help better identify the shape of it. Now, stem and leaf plots are constructed vertically. Once again, my stem is going from the smallest value and then all the way down to the largest value. But to properly describe the shape, what I'm going to recommend you do is I'm going to recommend you turn your stem and leaf plot on its side. Now notice I turned it on its side so that the stem almost serves as a number line. Now what I can do is I can see my leaves almost acting as if they are bars or possibly like a dot plot. That allows me to better identify the general shape of the values rather than when it's in its vertical pattern. Another really useful thing about stem plots is to compare two related distributions. For example, in this case, we were talking about male versus female literacy rates. So I can easily compare these two groups, the males and the females, by doing a back-to-back stem plot. Now it's important to recognize that in a back-to-back stem plot, you're going to use a common stem. So both the male data and the female data is going to be attached to the same stem in the center. Now what we're going to do is I'm going to show you not only how to have the females placed on here, but how to also have an additional data set placed on the opposite side. We already constructed our female stem plot on the right-hand side, so we're okay on that side. However, I'm going to identify my males on the left. Now it's important to see that on my graph, not only do I have data values, but I have them clearly labeled as to which group they pertain to. If I had this male-female portion covered up, it'd be really hard to be able to tell which side was going to be the males, which side was going to be the females. Now looking at our male data, I want to just remind you that the female stem ranged from 2 to 9. But if I look at my male data here and I split it into stem and leaves, you'll notice that my smallest male stem is a 5 and my largest male stem is a 10. So notice my stem ranges are different. But I have to label the back-to-back stem plot on a common stem. So what that means is I'm going to need to have my stem range from the smallest value to the largest value between both groups. So I'm going to add this 10 down here. So I go from 2 to 10. So I already have my female data labeled here. I'm going to now identify my male data. Now notice, just like a tree or a plant would grow larger as it gets further and further out, notice that our females, sure enough, gets larger as we go to the right, but notice that my males is the same, working its way to the left. All right, so you always want to grow as you go further and further away from the stem. All right, once again, my leaf unit is 1%. I have a nice title up here, as well as my two sides labeled. Now, a couple just kind of warnings and tips and tricks. Stem plots are really kind of tedious when it comes to large data sets, but there are a couple things that you can do in order to make larger data sets more manageable. The first modification that you can do is called splitting the stem. If you have a really large data set and you construct a stem plot, it's very likely that your leaves are going to be really far out from the stem. Now, the further and further your data gets out from the stem, the harder it is to really visually capture the shape of it. So what you commonly do with large data sets is you do something called splitting the stem, which means instead of writing each stem value just once, I'm going to write each stem value twice. So notice I have 2 zeros, 2 ones, 2 twos, etc. Now, what I'm going to do here is I'm going to show you an example of this data set and how to place it on a split stem graph. Now, to put these values, my leaves, on this graph, I'm going to put my leaves of 0 to 4, corresponding to the stem 0, in this first row, and I'm going to put leaves 5 through 9, corresponding to the stem of 0, in the second row. Now, it doesn't mean I'm going to have an equal number of leaves on each row. All it means that if there's 10 digits total, 0 to 9, and there's 5 in the first row, 5 in the second row, what that means is that each row has an equal chance of obtaining leaves. It doesn't mean that that certain data set is going to have an equal number per stem leaf or per stem row. And I'm going to do that for each split stem. So what I did is I took this data set and I split it up so that, sure enough, notice this is the number 1, 3, 5, 7, and 8. Instead of all of those values being in one row, what I'm doing is I'm putting digits 0 through 4 in the first row and digits 5 through 9 in the second row. Now, one thing that you can do with a stem and leaf plot is if you ever have a value, for example, down here, this 4 doesn't have any data in it. What I can do is if there's no data there, I can erase that. Now, it's important to note, however, though, that I cannot erase this middle section in the teens here. Okay, think of it as a branch. If you cut out the middle section of a branch, the rest of it's going to fall off. But you can trim off the edges, for example, before or after. This is our after portion if I had any empty spots up here. I can trim off the edges in order to help avoid a stem plot going on forever and ever and ever. Now, the second modification that you can do is called trimming. Trimming is a way of just helping manage your data so that if you have a lot of values, a lot of digits within each data value, that it's more manageable, meaning less digits to deal with. So for example, I might have a data set with a bunch of decimals, in this case 120.7. If I wanted to trim all the data, I might just chop off all the decimal places. And that is perfectly fine as long as you are consistent with your data. I can't just chop off this decimal place of this value and leave all the other decimals in my stem and leaf plot. You can also round if you would prefer. However, once again, please make sure you're consistent. If I rounded all my data sets, this would round to 121. Now, I know with these modifications, it's kind of hard to tell when you should split stems, when should you trim, etc. But it's also, I want to kind of ease your fears by letting you know that there is not one correct way to do a stem and leaf plot. Okay, use your judgment on deciding whether to split stems or whether to trim. All you need to do is clearly state what modifications you've made so that your reader can follow your work. All right, so let's check in on that. Number 1, Daniel and 7 of his classmates took the ACT test, a college entrance exam. The students' test scores were as follows. What would be an appropriate leaf unit for the data set? All right, number 2, identify the least value and the greatest value of the stem plot provided. Be sure to take into consideration the leaf unit provided when giving our answer. Okay, so We're going to shift gears now to histograms. We've talked previously about bar graphs, and histograms and bar graphs are very, very similar. There are actually two, I would say, main differences between them. Histograms represent quantitative variables, while bar graphs represent categorical data. Histograms show the distribution of counts or percentages among the values of a single quantitative variable. I mentioned that because we will talk about two quantitative variables later. And they are drawn with no spaces between the bars. Bar graphs, however, are categorical data, and they are drawn purposefully with a blank space between the bars, and that is important because you want to separate the categories so that you can see that they are in fact distinct groups. Here's an example of each. You can see the spaces on the bar graph, whereas no spaces on the histogram. All right, a couple histogram tips. How do you know what is a good bin width? When I say bin width, I'm talking about how wide you want to make the bars along the x-axis, meaning how many units do you want to go by? Well, there's not a perfect answer for that, but what I can tell you are a couple things you want to avoid and then give you some suggestions. For one, you want to avoid having too few classes. If you have a bunch of data crammed into only a couple bars, they're all going to be skyscrapers, these really tall bars. If you have a bunch of data spread out amongst a bunch of classes, you're going to end up with something called the pancake effect. You want to avoid either of these. In general, you have to say use your judgment. My general recommendation is to have between 5 to 10 classes, meaning bars, depending on how much data. The more data, you want to have more like 10. The less data, maybe more like 5. Important, when using a histogram to compare distributions, be sure to display the y-axis in terms of percentages rather than counts. We're going to talk later about comparing data sets to each other, and especially if you're trying to compare two groups, kind of like the mosaic plot. If you're trying to compare two groups of different sizes, you really don't want to try and use counts to compare them because they're not going to make sense. All right, so let's try one. I'm going to walk you through constructing a histogram, and then you'll have an opportunity to try it. The following IQ scores of 65th grade students chosen at random from one school are as follows. First step to construct a histogram is you want to divide your range of data into equal widths, so equal sized groups, not equal amounts of data, but equal sized units along the x-axis. Here's my hint. Find your smallest value, find your largest value, and then use the distance between those in order to figure out what increments you should go by based on how many bars you want to construct. So in this case, my smallest value is 81. My largest is 145. I can use that and say, all right, I want somewhere between 5 and 10 bars, or in this case, classes. Let me go by maybe tens. And go by tens, okay? So tens is going to be wide enough that I have data in each group, but it's not going to be skyscraper effect or pancake. Here's one thing you got to be careful. Don't double count any data values. For example, 85, you want to make sure you're very clear as to which class a data value that falls on the cusp of 2 would fall in. I like using inequalities so I can be consistent as to which side I include. All right, once you figure out what classes you want to go by, you can then fill out a frequency table. Basically, keep count of how many values fall in each class. So here's my classes. What I'm going to suggest is I'm actually going to highlight the left side of each class so that I tell myself that that is the side of the interval I'm going to include. Okay, really, I could have this say 75 to 85 as long as I make sure that I'm clear 85 goes in the second group, not the first one. All right, 85 is great. You just don't want to double count it. So I'm going to go through my data. I personally am a fan of I like to cross them off and kind of tally as I go so I don't accidentally lose any data along the way. And I could get some frequencies such as these. So here's my histogram. It looks very similar to a bar graph. The height of the bar has to do with how many data values fell in each class. Couple things, this little broken axis should actually be on the x-axis because notice I jumped ahead from 0 on the x-axis. It shouldn't be on the y because these are consistent going by tens. The bars are touching because one class numerically goes right up against the next class. In this case, I labeled the center of each class, but a lot of people will prefer to label the start and the end of each class. And then what they'll do is they'll just draw the bar in between them. That is fine as well. All right, go ahead, pause the video, and please try constructing a histogram of this data set. Make sure you label your graph entirely. All right, here we go. Go ahead and compare your histogram to this. I will say yours does not have to match perfectly because you might not have gone by the exact same class widths as I did. It's okay if yours looks slightly different as a result of choosing different bin sizes. Please make sure you're consistent though, don't double count, and label everything entirely. Here's some key features you'd want to make sure you include so you wouldn't lose credit. All right, it must be important because it's bright red, it's bold, and it's giant. Super important info alert. I'm going to start talking a little bit before we get to our last graph about examining distributions. What that means is anytime you're given a data set and you're asked to describe what you notice about it, there's some key features you want to discuss. You want to talk about the overall pattern and striking deviations. We reference the shape, the center, and the spread, as well as outliers when we're talking about those key features. A lot of people in AP, you will hear reference the acronym SOX. SOX, if you remember that, and you always reference those pieces, it stands for shape, outlier, center, spread. The order doesn't matter, but talking about each of them does. All right, so the shape has to do with the overall look of it. Okay, is it unimodal? Does it have one peak? Is it symmetric? Is it skewed one way or the other? When I say skewed left versus right, I'm talking about these options down here. Symmetric, we're relatively familiar with, but skew left and skew right are actually opposite of what you would naturally think. A lot of people look at this skewed left distribution right here and they immediately want to say skewed right because it looks lopsided to the right. However, it's opposite. Okay, the way I think about it is picture it as a mountain. My question to you then is, where would you draw the sun? So if the data is clumped on the right, it's actually, the sun would be on the left. I would say it's skewed left. Likewise with the skewed right, if the data is clumped on the left, sun would be drawn on the right, it's skewed right. All right. Center and spread we'll talk a lot more about in our next video. We will reference center typically by mean or median, and spread by some measurements referenced as range and IQR or standard deviation. We haven't gotten there yet, but I want you to know that those are the general features that we're going to be discussing. Shape, center, spread, and outliers are any unusual points that maybe pop up in your data set. You should always be looking for if there might be a reasonable explanation for them, but when in doubt, identify them as a point of concern and why you think they might be there. All right. Here's a little snapshot. I'm going to go ahead and screenshot this, and I'm going to try and send this out to you once you have a chance to view the video. This is a really important, just general summary of the things that we need to describe. Notice we have a lot of different ways we can describe shape: approximately symmetric, skewed left, skewed right, unimodal, bimodal if there's more than one peak, two modals. Uniform is if it's relatively flat all the way across. Center and spread, which measurement we use is a direct result of the shape that we choose. Again, we're going to hit on this in our next video. And outliers, as of now, I want you to just use your judgment and explain your reasoning. However, I will give you an outlier rule coming up soon. All right, last but not least, we're going to talk about an ogive. It looks like ogive, I know, but it is ogive, I promise. Another word for it is relative cumulative frequency graph. It's going to be very similar to a histogram, but one extra step. So we're going to start off with this data set and construct a histogram, essentially. I've broken it up into classes already. I am now going to count how many data values fall in each class. This is the count right here. This is just the percent. That's all that means. Count and percent. Relative frequency has to do with the percentage. I could take this information and construct a histogram. In fact, this x-axis should be broken because we jumped ahead to the number 39. Histograms are great. It gives you a really good picture of the data set, except the issue here is, what if I asked you a question about a particular data value? Where does Clinton fall relative to the other presidents? Well, I know he falls somewhere in here, but the question is, where? I don't know, somewhere in there. That's where an ogive comes into place. Ogive is going to have us go one step further. Instead of looking at the individual frequencies of each class, we're going to look at the cumulative frequencies of each class, sorry. So the cumulative frequency of the first class is still going to just be 2. Cumulative just means that and everything before. So there's still only 2 values in that first class because there's nothing before it. But the cumulative frequency in the second class that originally had 6, cumulatively, there's actually now 8 values, the 6 and the 2 before it. In this next class, we originally had only 13 values in it specifically, but now if I add the 6 and the 2, the cumulative frequency is 21. So instead of plotting the individual frequencies or individual percentages, we're going to plot the classes with the cumulative percentages or the relative cumulative frequencies. All right, so let's put these two kind of together. What we're going to do when we plot this is we're going to plot a point corresponding to the relative cumulative frequency, the cumulative percentage, in each class on the right side of the interval. Let me show you what this looks like. All right, so I have my classes. I started at 40, and I'm going to start at 0% because there was no data before 40. By the time I get to the end of that first class, I had 2 data values. 2 out of the entire data set, I want to say was about 4.7%. So sure enough, that's where I put this first dot at the end of the first class, 4.7%. By the time I got to the second dot, I want to say I was at about 18%. So I plotted that. I'm moving left to right, and I'm just plotting the cumulative percentage. By the time I get to the end, I should always be at 100 because by the time I get to the end, I should have covered all of the data. Why is this so helpful? Because now I can find an individual in the data set. What percent of US presidents were younger than Bill Clinton? Well, I know Bill Clinton was 46, so 46 falls about there. Not only can I figure out where he falls age-wise, but I can now match that up with his percentile. It looks like about 10% of presidents were younger than Bill Clinton. So in turn, what if I ask you what percent are older? Well, if 10% are younger than Bill Clinton, 90% must be approximately older than him. But here's the thing, we can use it both ways. Check this out. All right, what about this? About 20% of presidents were older than what age? So not only can I go from the x-axis, follow it up and over to the relative cumulative frequency, but if I know a percentile, if I know a percentage, I can follow it over and down as well. So if I want to know about 20% of presidents were older, so that really means 80% were younger, 20% older, 80% younger, then what age when they were inaugurated? Let me follow that over to my ogive and follow it all the way down. It looks just a little bit above 60, so I'm going to estimate here. I'm going to say about 60, 61. Okay, there we go. So about 20% of presidents were older than 61 when they were inaugurated, which means about 80% of presidents were younger than 61 when they were inaugurated. All right, here's our last U-Try for you. 2 problems, both having to do with the exact same ogive. It says grade point average for a large public high school. We have our GPA on the x-axis. We have our cumulative proportion, also known as relative cumulative frequency, on the y-axis. Go ahead and answer number 1. What is the median grade point average? Median, you do have to know, median is like the 50th percentile, the middle. All right, there we go. So I'd say about a 2.4, working backwards from the percentile. Number 2, Joe earned a 3.2. What percent of the school beat him? Ooh, beat him. So he got a 3.2, so I got to find 3.2 is about there. What percent got higher GPAs than him? Not lower, but higher. There we go. 0.9, so 10% got higher than him, beat him. 90% got lower than him. Typically, A is the most commonly missed option for a question like that because people forget that they need to think about the higher GPA, not the lower GPA. All right, there we go. That is topic 2. That should say quantitative data. Sorry about that. Hopefully you feel like you can do graphical displays for quantitative data, dot plots, stem plots, histograms, and ogives. Identify the shape of quantitative distributions, skewed right, skewed left, relatively symmetric, uniform, all those descriptors. And we're going to talk some more about our numerical measurements for describing these distributions coming up soon. Otherwise, have a great day.